Hi, greetings from the Technical University of Catalonia in Barcelona, Spain. This is Sergio Busquets Monge, and I will be delivering the second part of this tutorial. We will cover the last two sections, sections 3 and 4, where we will discuss in detail virtual vector pulse-width modulations for NPC multilevel converters and some application examples. Let's jump into section 3. In this section, we will cover the following points. We will first have an introduction to review very basic concepts. Then we will jump to DC to AC conversion at the minimum number of levels, which is 3, to see how virtual vector pulse-width modulations can be defined in this case. Then in subsection 3.3, we will see how to extend these virtual vector pulse-width modulations to n levels. In subsection 3.4, later on, we will see some alternative pulse-width modulations that also guarantee capacitor voltage balance. And we will finalize the presentation by seeing how to extend this approach to DC conversion. Before we proceed with the introduction, let me just mention that in many slides you will see a reference number on top, in the top right corner. In these references you will be able to get deeper into the concepts presented in the slide, and the details of the references are listed at the end of the presentation. So, well, as you all know, the two-level leg topology, widely used in many converters, is functionally equivalent to a single-pole double-throw switch, as represented here in the left. We have an AC terminal that can be connected to two DC link points, DC1 and DC2, and the position of the switch is telling us to which terminal the AC terminal is connected. An alternative representation is shown here in the right. The AC terminal can be connected to the two DC link points, and the possible connections are indicated with these void circles. And the effective connection is indicated with a solid circle. We will use this notation for convenience in the following. The implementation of the two-level leg can be done by using two switches with anti-parallel diodes. So what is an M-level NPC leg? Well, it can be regarded as an extension to a higher number of DC link points of the two-level leg. So an N-level NPC leg will be functionally equivalent to a single-pole multi-pole throw switch. The AC terminal can be connected to the outer DC link terminals, DC1 and DCN, but also we will have available a series of inner DC link points to which we will be able to connect the AC terminal. These inner DC link points are known as the neutral points, and that is why we call this topology the NPC, okay, the neutral point clamp, because we can clamp or connect the AC terminal to these neutral points. How can we implement this neutral point clamp leg? We have several options. The first one is to use a single switch with anti-parallel diode and use this type of pyramidal connection. All devices will be the same with the same voltage rating. This is called the active clamp or transistor clamp topology. An alternative implementation can be achieved by eliminating the switches inside the pyramid. This way we obtain what we call the passive clamp or diode clamp topology. All devices still have the same voltage rating. If we want to simplify the topology by reducing the number of components, the number of devices, we can combine some of them and use switches and diodes with higher voltage rating. This is what we do in the reduced active clamped version of the topology, where we basically combine several active switches into others that have higher voltage rating. And this way we reach the T-type topology at 3 levels, the pi-type topology at 4 levels, and so on. But the price we pay for reducing the number of components is that we need to use different voltage ratings for the different devices. Similarly, we can also combine some of the diodes in the passive clamp topology to reduce the number of diodes and reach the reduced passive clamp version of the topology, which is the topology widely appearing in the literature. Okay. In this case, we will have lower number of diodes as compared to the regular passive clamp topology, but some of them will have higher voltage ratings. In any case, regardless of the selected topology that we use to implement the NPC legs, they can only always be regarded as a single pole multiple throw switch from the modulation point of view. In a first approximation, when we develop pulse width modulation strategies, we can model these NPC legs as single pole multiple throw switches, and we don't need to really know the details of the selected implementation. So let's now see how we can define a suitable modulation strategy using these NPC legs. We will focus on a popular case, which is the 3-level, 3-phase DC to AC converter. This converter is built with 3 legs, and on the DC side we will have a DC source or load followed by a series connection of capacitors to define the 3 DC link nodes. And then on the AC side we have an AC load or source. The converter has 27 switching states, converter switching states, that define the vectors of the space vector diagram. These vectors are located in the plane of differential or line-to-line voltages. And when we focus on the first sextant of this space vector diagram and we indicate the value of the neutral point current associated to each converter switching state, we realize that some converter switching states introduce a neutral point current different than 0. As you all know by now, a neutral point current different than 0 implies that we will generate an imbalance of the DC link capacitor voltages from a pre-existing balance condition. So we need to figure out how to use these switching states so that they overall do not modify a pre-existing balance condition in the capacitor voltages. How can we do this? Well, one option is to redefine the vectors in the space vector diagram, and we can redefine them as shown here in the right, defining what we know as the virtual vectors, as a set of virtual vectors. These virtual vectors are defined so that they all have an average neutral point current over the switching cycle equal to 0. For instance, this virtual vector here is defined as 1/2 of switching state 221 plus 1/2 of switching state 332. This means that whenever we want to apply this virtual vector for some time, 1/2 of this time we will use switching state 221, and the other half we will use switching state 332. Since the neutral point current of both switching states is the same but opposite in sign, overall when we apply this virtual vector, we will generate a 0 average neutral point current. And same thing happens for the remaining virtual vectors. So if we use these virtual vectors to approximate the reference vector, we will guarantee that the average neutral point current is equal to 0. So we will use these virtual vectors to approximate the reference vector. The reference vector, noted here as V star, represents the desired set of line-to-line voltages we want to achieve at the AC side. Okay? This virtual vector is defined with a length equal to the modulation index, and here the modulation index is defined as the peak value of the line-to-line voltage divided by the DC link voltage, and it has an angle equal to the line cycle angle. We need to approximate this reference vector by a set of virtual vectors, and typically we use the virtual vectors of the vertices of the triangle where the reference vector is located. By approximating the reference vector from these virtual vectors, we will come up with a duty cycle for each virtual vector. Okay, the coefficients of this linear approximation are the duty cycles or the duty ratios that we need to apply each virtual vector. And then we can compute the duty cycle of all relevant converter switching states by simply applying the corresponding coefficients of the linear combinations defining each virtual vector, and this way, and we will get then the duty cycles of the converter switching states. Once we know the duty cycles of the converter switching states, we just need to define what will be the sequence of application of these converter switching states. Typically, we define this sequence so that we minimize the number of switching transitions, and so that we also achieve a symmetrical pattern over the switching cycle. And once we order the converter switching states this way, we can note that each leg follows the same switching sequence. If we look into each leg, we will see that they start connecting to point 1, then they move to connect to point 2, and then they move to connect to point 3, and then we have the reverse sequence. By noting this, we realize that a very simple implementation of this modulation strategy could be achieved by simply forcing this pattern for each leg and knowing the duty cycles of connection of each leg to each DC link point. But you may think, well, but maybe the pattern of these leg duty cycles of connection to each DC link point are very complex, so this will not be a very efficient implementation of the modulation strategy. But it turns out that these duty cycles are very simple. Here we can see the patterns of these duty cycles for leg A under different modulation indexes. As you can see, the pattern is very simple. Both DA1 and DA3 follow like somewhat like a McDonald waveform. So they are portions of sinusoids put together. DA3 is the same as DA1, phase shifted 180 degrees, and DA2 can be obtained by simply knowing that the addition of these three duty cycles is equal to 1. So the pattern is very simple. The duty cycles for legs B and C are the same as for leg A, but phase shifted plus minus 120 degrees. And in fact, we can get the value, the exact value of these duty cycles by some very simple expressions. We start with the normalized value of the phase voltages, which are written here as dA, dV, and dC. These are sinusoidal functions, phase shifted plus and minus 120 degrees. And then from these values, we can compute directly dA1 as the maximum of dA, dV, dC minus dA. dA3 can be computed as dA minus the minimum of dA, dV, and dC. And dA2 can be obtained simply as 1 minus dA1 minus dA3. So yeah, you can see that by using these very, very simple equations, we can implement the modulation strategy without having to deal with any space vector diagram related calculation. Once we know that the modulation strategy can be defined with these simple duty ratio waveforms, we can quickly and simply verify that the modulation strategy guarantees capacitor voltage balance. And we can do this by simply computing the neutral point current from the value of these leg duty ratios. The neutral point current will be the contribution of leg A plus the contribution of leg B plus the contribution of leg C. And since the modulation strategy forces that dA2, dB2, and dC2 are equal, because when we phase shift this waveform 120 degrees, we get exactly the same waveform, then we can take common factor dA2, and then this is multiplied by the addition of the three-phase currents, which are equal to 0, which is equal to 0 because the load has an isolated neutral. And therefore, we get a value of the neutral point current equal to 0. We can also implement this modulation strategy carrier-based. We just need to define two modulation waveforms and one carrier per leg. Modulation A1, we will consider here in the slide the case of leg A. Modulation A1 is simply dA1, and modulation A2 is simply the addition of dA1 plus dA2, which is the same as 1 minus dA3. And then the rule to define the modulation strategy based on this carrier and modulating waveforms is the following. Whenever the carrier is below both modulating waveforms, like here, we will be connecting to point 1. Whenever the carrier is between the two modulating waveforms, we will be connecting to point 2. And whenever the carrier is above the two modulating waveforms, we will be connecting to point 3. So the modulation strategy becomes very, very simple to implement. And in fact, the switch control signals for the topology can be derived directly from this, from the comparison of the carrier to the modulating waveforms. We can see this very quickly with the simple case of a diode clamp 3-level leg. In this case, the control signal for this switch could be obtained comparing the carrier to modulating signal mod A1. This comparison will define the control signal for the switch. Then, by comparing the carrier to the modulating signal A2, we will obtain the control signal for the switch, and then the control signals for the other two switches will be the complementary signals. This will be the complementary signal of this one, and then this will be the complementary signal of this switch, okay? This is the complementary signal of this one, and this is the complementary signal of this one. In the following slides, we will see how this pulse width modulation strategy, the virtual vector pulse width modulation strategy, compares to another strategy, another NPC strategy, conventional nearest three-vector pulse width modulation strategy, where we use all switching states for each vector. This NPC pulse width modulation strategy that uses all switching states for each vector has the property of generating the minimum harmonic distortion at the AC output. So it is a quite competitive strategy because of this feature, okay? Well, it turns out that at low modulation indexes, both the virtual vector and the NPC strategy are the same. So this means that our virtual vector pulse width modulation at low modulation indexes will have an optimum harmonic distortion, the minimum one. At higher modulation indexes, the two strategies differ, and we can see clearly this because the duty cycles, the leg duty ratios are different in one case and the other. okay? And well, it turns out that while the virtual vector pulse width modulation can reach capacitor voltage balance for all values of the modulation index and the load angle, the NTB pulse width modulation strategy is not capable of reaching capacitor voltage balance in every switching cycle for high modulation indexes and high load angles specifically in general. But we pay a price to achieve this benefit of capacitor voltage balance in all operating conditions. And the price we pay compared to the NTB strategy is that we have to increase the number of switching transitions per switching cycle, especially at high modulation indexes. And also at high modulation indexes, we need to increase the harmonic distortion of the line-to-line voltages. However, despite the fact that we need to increase the number of switching transitions, and we will have higher switching losses, obviously, the thermal stress does not increase that much because the virtual vector pulse width modulation, in fact, what it is doing is it's kind of using the switches for a longer portion of the line cycle, while the NTB pulse width modulation is using switches for half of the switching cycle of the line cycle, and then those switches stop switching for half of the line cycle. The virtual vector pulse width modulation extends the portion of the line cycle that switches are switching, and therefore we can expect lower variations of temperature. The average temperature may rise, but the variation of temperature may be lower because of this. So overall, the thermal stress will not increase that much, okay? May not increase that much. So far, we have defined a virtual vector pulse width modulation that is able to keep the capacitor voltages balanced in every switching cycle for any value of the modulation index and for any load, with the only requirement that the addition of the three-phase currents equals to 0. But however, we have also seen that this is achieved at the expense of an increased harmonic distortion compared to conventional NTB pulse width modulation. So the question now is, can we do better? That is, can we obtain a new virtual vector pulse width modulation that is also able to keep capacitor voltages balanced, and with a lower harmonic distortion, and maybe even lower number of switching transitions? In order to answer this question, we can formulate a general pulse width modulation strategy based on some generic virtual vectors defined as a linear combination of switching states, but now the coefficients of this linear combination are unknowns. We have designated these unknowns as R1 through R7. This generic pulse width modulation covers all relevant pulse width modulation strategies, like the nearest three-vector pulse width modulation that we can obtain by forcing R5 and R7 equal to 0, or the virtual vector pulse width modulation that we will obtain if we force the value of the unknowns to be this. So basically, this generic pulse width modulation looks like can lead us to interesting optimized pulse width modulations. If we find the values of the unknowns in every switching cycle through mathematical optimization algorithms to minimize harmonic distortion in the case of a linear load, we obtain the leg duty ratio patterns that shown here. For a load angle of 0 degrees, we obtain a similar duty ratio pattern as we had in the initial or original virtual vector pulse width modulation, but the waveform is softer. Note that whenever the load angle is different than 0, the leg duty ratios vary, and the leg duty ratio waveform depends therefore on the load angle. This didn't happen in the initial virtual vector pulse width modulation because in that case we had the same duty ratios no matter what load we were using. So this can be regarded as some disadvantage of this optimized virtual vector pulse width modulation. Anyway, if we compare the performance of this new optimized virtual vector pulse width modulation to the initial or original virtual vector pulse width modulation, we can clearly see that while both strategies can keep the capacitor voltages balanced in every switching cycle, the new optimized virtual vector pulse width modulation presents a much lower distortion than the original. In the literature, one can find other variants of the initial virtual vector pulse width modulation. For instance, in reference 7, the authors use a different definition of the virtual vectors. In other references, they combine NTV pulse width modulation with virtual vector pulse width modulation to define hybrid PWM strategies. Well, the pulse width modulations we have seen so far keep the capacitor voltages balanced. But in a non-ideal world, we will have some non-idealities that will cause imbalances in the capacitor voltages. For instance, if we have a driver of a switch that is misbehaving, this can lead to a different duty ratio than desired for this switch, which can also then lead to obtain a leg duty ratio that is not the value we were intending. And this obviously can lead to capacitor voltage imbalance. Another reason for which we can get capacitor voltage imbalance is that the impedance across the two DC-link capacitors may be different. Or even we could have some leakage current through the load neutral that could cause this capacitor voltage imbalance. For all these reasons, we need a closed-loop control of the capacitor voltages. We may even need to operate in some applications with different capacitor voltages, and for this reason, to adjust the voltage of each capacitor to the desired level, we will need this closed-loop control. The closed-loop control of the capacitor voltages is based on the effect of the neutral point current. In the bottom of this slide, we analyze in detail the effect of the neutral point current in the capacitor voltage imbalance. The neutral point current can be expressed as the addition of this current I to D plus this current I to U, which are the currents flowing through the two capacitors. And then, through the characteristic equation of the capacitors, we can express these currents in terms of the capacitor voltages. Gathering terms, we end up getting the expression here, where we can see that the neutral point current is defining the derivative of the difference between the two capacitor voltages. We can call this difference, VC1 minus VC2, as the voltage imbalance at point 2. So what we see clearly is that the neutral point current is defining the derivative of this voltage imbalance. So based on this, we can propose a very simple closed-loop control of the capacitor voltages. On one hand, we will have the command of the voltage imbalance, which will be compared to the measured voltage imbalance, and this will define an error that can go through a PI compensator to define a command of the neutral point current. Afterwards, to reach this value of the neutral point current, we can proceed several ways. One way is to get a normalized value of the neutral point current by dividing by 2P divided by DC, where P is the power flowing from the DC to the AC side. This normalized value, we call it here K2. And with this normalized value, we can modify the leg duty ratios to introduce the desired neutral point current. We just need to simply multiply dx3 by 1 plus K2, multiply dx1 by 1 minus K2, and then the value of the duty cycle of connection to point 2 can be computed knowing that the addition of these 3 leg duty cycles must be equal to 1. The resulting waveforms with the application of this parameter k are shown here in the slide. For k equal to 0, we have the same waveforms as we had presented before. And whenever the value of k is positive, as you can see, the duty ratio dA3 goes up and the duty ratio dA1 goes down. We have the reverse behavior whenever the parameter k2 is negative. Essentially, what we are doing by applying this coefficient k2 is to introduce a common mode voltage in the leg voltages. In this simulation, we can check the good performance of this closed-loop control. Initially, in the simulation, both capacitor voltages, the command of these 2 capacitor voltages are the same. They are set at 50 volts. And the real capacitor voltages follow the references since we are using the virtual vector pulse width modulation. At this point in time, we separate the references for voltage of capacitor 1 and capacitor 2. We make the voltage of capacitor 1, the reference, the command to be 60, and the other one is 40. And basically, the closed-loop control makes sure achieves a real capacitor voltage matching the reference, the command. Notice that the variation of the leg duty ratios is very slight to achieve this control. Finally, at this point in time in the simulation, we recover a command for the voltages so that both are equal to 50 volts. And as we can see, the control is able to recover this balance without too much variation of the leg duty ratios again. Well, an important feature of this pulse width modulation strategy, as you can see from the simulation, is that regardless of the value of the capacitor voltages, we cannot see any specific low voltage, low frequency distortion in the phase currents. We can operate with different capacitor voltages and we see no distortion, or we see no difference, almost no difference in the leg currents. This is a very interesting property of this modulation strategy that will enable us to operate with different capacitor voltages, which is interesting in several applications. Let's now discuss the operation with this virtual vector pulse width modulation in other situations and in other conditions. We'll start by discussing the operation in the overmodulation range. Well, as you know, with any type of a space vector diagram, we can only approximate properly the reference vector if this reference vector falls within the hexagon of the space vector diagram. If the trajectory of the reference vector goes beyond the hexagon, like is shown here with this trajectory with with a dotted black line, then we will have to find out a way to approximate this trajectory, and we will not be able to approximate properly the reference vector when it goes beyond the boundary. If it is slightly exceeding the boundary, what we can do is to follow this alternative red trajectory that starts with a circle trajectory until the crossover angle, and then we follow the boundary, the hexagonal boundary. The fundamental component produced by the red trajectory will be the same as with the black reference vector trajectory. but obviously we will be introducing some low frequency harmonics. As we increase the radius of the reference vector trajectory, as we increase the amplitude of the output AC voltages, the crossover angles goes from 30 degrees to 0. When we reach a crossover angle of 0, if we want to increase the amplitude of the output voltages, we must move to overmodulation mode 2, where we basically, what we do here is we keep the converter switching state of the vertex of the hexagon for some holding angle, and after that we follow again the hexagonal boundary. The holding angle, as we increase the amplitude of the output voltages, goes from 0 degrees up to 30 degrees. So this is how we proceed with a two-level three-phase converter when we want to operate in the overmodulation region. And in a three-level converter, we can do exactly the same. The problem is that when we follow the hexagonal boundary, the real one, then the duty ratio of connection to the neutral point is 0. And this gives us no margin to regulate the capacitor voltages whenever we need to decrease this duty ratio, because it is already 0, we cannot make it smaller. So in order to have regulation margin, in order to be able to decrease the duty ratio of connection to the neutral point, we will operate with a virtual boundary, shown here in red, and we will follow this boundary in the overmodulation region, guaranteeing then that the duty ratio of connection to the neutral point will always be higher than 0. In the next slide, we can see the operation in the overmodulation region following this strategy. We can see that in both overmodulation regions, the capacitor voltages are balanced, but as expected, because it's typical from the operation in the overmodulation region, we can see low frequency harmonic distortion in the output three-phase currents. Okay, let's now see how we can extend the virtual vector pulse-width modulation to the low frequency modulation index range. So the goal here is to see how we can extend this virtual vector pulse-width modulation to carrier frequencies or switching frequencies that are not far away from the line frequency. The virtual vector pulse-width modulation we have seen so far was defined with the assumption that the phase currents, the leg currents, were almost constant along the switching cycle, and this is only true when the carrier frequency is much higher than the line frequency. How do we extend then this modulation strategy to low frequency modulation index values? Well, we can basically apply the same voltage pattern we generate with the carrier-based implementation of the virtual vector pulse-width modulation, but the only detail is that we need to set the MF factor, which is the carrier frequency divided by the line frequency, to an odd integer value multiple of the number of phases. We will need to make sure that MF is an odd integer multiple of the number of phases. We need MF to be an odd integer because this way we will force half-wave symmetry in the output voltages, and this will eliminate all even order harmonics. And we want MF to be a multiple of the number of phases because then we will obtain the same leg voltage pattern in all legs. So for example, in a three-phase converter, we could set MF to 3, 9, 15, and so on. If we set MF equal to 3, we obtain the leg voltage pattern with the minimum number of switching transitions per fundamental cycle. This is the pattern shown here with this blue waveform. We have one positive pulse and one negative pulse. The shape of the voltage, of the leg voltage, has only 1 degree of freedom, which is this angle alpha that defines the width of the positive pulse and the width of the negative pulse. In the bottom of this plot, we show the leg current, which is plotted decomposed into a component in phase with the fundamental component of the leg voltage, which will look something like this, and then a component in quadrature of the with the fundamental component of the leg voltage. The fundamental component of the leg current can always be represented as the addition of these two components. The blue areas in these waveforms represent the charge injected into the neutral point. When they are above the horizontal axis, they are positive charge. When they are below the horizontal axis, they are negative charge. As you can see, all areas cancel, so that the total charge injected into the neutral point is 0. And this means that we will not unbalance the capacitor voltages. So angle alpha in this modulation strategy is only defined by the desired value of the modulation index, or which is the same by the desired amplitude of the output voltages, while keeping the capacitor voltages balanced, obviously. So far we have seen the case of a three-phase converter, which is a very typical case. Let's now see how we can extend this pulse width modulation to other number of phases. We will start with the single phase case, and then we will move to the case with a number of phases higher than 3. The single phase case is represented here with a converter using two legs, so that we are forcing voltage VAB across the single phase load or source. This case has a space vector diagram that can be represented in a single line corresponding to the differential voltage divided by VDC. This will be the normalized differential voltage. Since we have two legs, we have 3 times 3, 9 converter switching states that define the 9 converter switching states in the space vector diagram, with a total of 5 vectors. Some of these switching states have a non-zero neutral point current, so we can proceed as we did with the three-phase case and define some virtual vectors with an average neutral point current equal to 0. And when using these new virtual vectors and defining pulse width modulation with them, we obtain a pattern for the leg duty ratios as shown here. They are even simpler than in the three-phase case. Pay attention that the duty ratio of connection to point 1 and 3, now they are just simply portions of a sinusoidal function. DA2 again can be obtained knowing that the addition of the 3 duty ratios is equal to 1. In fact, the leg duty ratios can be obtained in following the same approach we did for the three-phase case. We first write down the normalized value of the leg voltages, dA and dB, and then dA1 can be computed as the maximum value of dA and dB minus dA. dA3 is equal to dA minus the minimum value of dA and dB, and dA2 can be obtained knowing that the addition of the 3 duty cycles will be equal to 1. Leg B duty ratios will be the same as leg A duty ratios, but phase shifted 180 degrees and can be computed with the same type of equations as here. This is how this single phase pulse width modulation performs. We can see now that we have a simple commutation pattern in both the leg voltage and the differential voltage across the load. How can we extend the virtual vector pulse width modulation to more than 3 phases? Well, here we're showing a particular case, the five-phase case. We can proceed exactly the same as we did with the 3-phase and the single phase. We first write down the normalized value of the phase voltages, and then we compute the duty cycles of each leg connecting to each of the ECCE points, following the same expressions. The resulting leg duty ratios look a little bit different, but essentially the approach is exactly the same. And it can easily be extended to any number of phases. We just need to follow the same approach. Exactly the same approach. Let us now see how we can extend this virtual vector pulse width modulation to an arbitrary number of levels higher than 3. In the slide, we can see as examples the 4-level case and the schematic of the 5-level case. In order to guarantee capacitor voltage balance, the virtual vectors must ensure that all neutral point currents are equal to 0 on average over the switching cycle. So for instance, in the 4-level case, each virtual vector must ensure that both I2 and I3 are equal to 0. It turns out that we can define these virtual vectors for all number of levels. Here in the bottom of the slide, you can see the location of these virtual vectors in the first sextant of the space vector diagram for the 4-level case and for the 5-level case. If we use these vectors to define a pulse width modulation strategy, surprisingly, the leg duty ratio waveforms we obtain are very similar to the 3-level case. In fact, the leg duty ratio waveforms of connection to the outer ECCE points, DA1 and DAN, are exactly the same as in the 3-level case. The only difference is regarding the duty ratio of connection to the neutral points. The duty ratio of connection to the neutral point in the 3-level case is now split into all possible neutral points. We can also implement this pulse width modulation carrier-based. We just need to use n-1 modulating waveforms and 1 carrier per leg. And also the rule to apply this modulation is analogous to the 3-level case. We just need to count the number of modulating waveforms below the carrier to know to which point the leg is connecting. The switch control signals, again, can also be obtained by comparing the carrier to the modulating signals. We can also extend the pulse width modulation strategy to a low value of the frequency modulation index. So that is to carrier frequencies close to the line frequency. Here in the slide we can see the voltage patterns for the minimum number of switching transitions, which are obtained when we set MF to 3. These voltage patterns, we get them by from the carrier-based implementation of the modulation strategy, as we did for the 3-level case. While in the 3-level case we had a fairly simple voltage pattern, now in the 4-level and 5-level cases we see that the voltage pattern is slightly more complex. It is in fact including a zigzag between the positive half cycle and the negative half cycle that we didn't see in the 3-level case. This zigzag in the leg voltage is necessary in order to reach capacitor voltage balance. In the slide, the charge injected into the neutral points is indicated with colored areas, with one color for each neutral point. For instance, in the 4-level case, red areas represent the charge injected into the neutral point 2, while green areas represent the charge injected into neutral point 3. In order to keep capacitor voltages balanced, we need to force that all areas with the same color add up to 0. And the design variables for the modulation, which are these switching angles alpha, should be selected so that these areas add up to 0. We will define these switching angles based on this, and also to force that the amplitude modulation index M is equal to the value we want. In the general N-level case, we can clearly see this zigzag in the leg voltage pattern. That again, it is necessary so that we can keep all capacitor voltages balanced. Let's now move to see how we can extend the closed loop control of the capacitor voltages to the general N-level case. Now we have more than one neutral point, and therefore we will have to deal with more than one neutral point current. Each neutral point current is affecting the DC link in a different way. In the 4-level case, we have two neutral point currents, I2 and I3, and according to the analysis shown here in the slide, which is analogous to the analysis we did for the 3-level case, we can conclude that neutral point current I2 is forcing the derivative of the voltage imbalance at point 2, which is calculated as the difference between the bottom capacitor voltage and the average value of the top two capacitor voltages. And on the other hand, I3 is forcing a variation or derivative of the voltage imbalance 3, which is defined as the difference between the average value of the two bottom capacitor voltages minus the top capacitor voltage. From this analysis, we can then propose the closed loop control of the DC link capacitor voltages with two loops, okay? One loop for each neutral point. Similarly to what we did for the 3-level case, but now since we have two neutral points, we will have to add two loops. One loop is in charge of controlling the value of the voltage imbalance at point 2, while the other loop is in charge of regulating the voltage imbalance at point 3. Each loop is defining the reference or command value for the neutral point currents that we will later on be able to achieve by modifying the duty ratios in a similar way as we did for the 3-level case. But the problem is that the two loops are not independent. They are coupled. This means that when I inject current I2, I will not only be affecting the value of voltage imbalance 2, but also I will be affecting the value of voltage imbalance 3, as it is shown here in the slide. The variation of voltage imbalance 3 is half the variation of voltage imbalance 2, therefore the effect on voltage imbalance 3 of I2 is smaller, but still we need to take into account this coupling in order to produce the best closed loop control performance. To avoid this coupling affecting the closed loop control performance, we need to introduce a decoupling matrix here at the output of the two control loops. Basically, we will multiply the output of the two control loops by this decoupling matrix, and then this will define the reference value of the two neutral point currents. If we consider the plant, which has coupled coupling between the two control loops, together with this decoupling matrix, we will obtain a virtual plant that where all the two control loops are decoupled, and therefore these controllers can operate as if they were completely independent. In the following, we will see some simulations to analyze the performance of these virtual vector pulse width modulations. Well, in both the 4-level and 5-level case, we can see that a characteristic of this virtual vector pulse width modulation is that by looking at the leg voltage, we can see that for 120 degrees, 60 degrees here and 60 degrees here, the leg is connecting to all possible DC link points. This is a characteristic feature of this pulse width modulation strategy. When we analyze the total harmonic distortion of the line-to-line voltage, we see that as we increase the number of levels, the THD decreases at low modulation indexes, but it remains more or less the same at high modulation indexes. This is because at high modulation indexes, we need to make an extra effort to keep the capacitor voltages balanced, and this then does not allow us to keep decreasing the THD values at these levels. In this simulation, we compare the performance of the control with decoupling and without decoupling. The reference value of all three capacitor voltages start being the same, and at some point in time, we change the reference value for C2 voltage and for C3 voltage, while keeping the reference value for capacitor C1 voltage the same. As we can see with the control with decoupling, the voltages follow the references without problems. But if we use a control without the decoupling, what happens is that voltage, the capacitor C1 voltage changes, although the reference didn't change. This strange behavior is due to the coupling of the two control loops that we didn't take into account while implementing the closed loop control. Again, please note that despite having the three capacitor voltages being different, we don't see any significant distortion in the currents whenever we operate with different capacitor voltages. So with this, we finish the discussion of virtual vector pulse width modulations in the DC to AC conversion case. You may ask yourself if we can conceive alternative pulse width modulations following different approaches. And the answer is yes. Okay, we can relax the constraint on the neutral point currents, and instead of forcing it to be zero on average over the switching cycle, we can force it to be zero over a longer portion of the line cycle. And by doing this, we will be able to get some advantages regarding harmonic distortion and switching and number of switching transitions. This is the case of the so-called carrier overlap pulse width modulation, which is a modulation strategy defined for the 4 levels, for 4-level case. It is implemented using a modulating waveform, a single modulating waveform in blue, compared to 3 triangular carriers. The modulating waveform contains a sinusoidal component and a common mode component so that we can obtain the maximum line-to-line amplitude in the linear modulating range. The triangular carriers, 2 of them, the red one and the violet one, are level shifted, and the third one, in green, overlaps the other 2. The rule to apply this modulation is to count the number of carriers below the modulating waveform, and this will tell us to which point we need to connect the leg at each point in time. The resulting leg voltage pattern is shown here in blue, and we can notice that during these 60-degree periods, where the virtual vector pulse width modulation had connections to all DC link points, now we only have connections to 3 DC link points. So we can already see that this pulse width modulation will present a lower number of switching transitions compared to the virtual vector pulse width modulation. In this simulation, we can see that the outer capacitor voltages, VC1 and VC3, present a low frequency component. They oscillate at 3 times the line frequency. This means that we will have to introduce in the DC link a higher capacitance compared to the virtual vector pulse width modulation if we want to keep the ripple of these capacitor voltages below a limit. But in exchange, we can improve some other performance features such as the line-to-line harmonic distortion, as we can see also in the simulation. The harmonic distortion will be lower compared to the virtual vector pulse width modulation, together with the decrease in the number of switching transitions we have seen before. And this concludes the section regarding DC to AC conversion, and we should now move to the DC to DC conversion case. However, due to the lack of time, we will not get into the details of this case. You have the details of the basic operation in the slides. And I will just mention that we can also build DC to DC converters with NPC legs and any number of levels. We can build DC to DC converters without galvanic isolation, as shown here, combining 2 NPC legs and a DC link formed by a series connection of capacitors. And we can operate this converter while keeping all capacitor voltages balanced. The voltage, the DC voltage of the B side can be either higher or lower than the DC voltage of the A side, so the converter can operate in both boost and back modes. We can also build converters, DC to DC converters with galvanic isolation, and we can achieve this through a dual active bridge multi-level topology. Basically, the converter here is built with 2 DC links and 2 pairs of NPC legs on each side, and then finally a high frequency transformer in the middle. And this basically finishes section 3. So at this point, I would like to conclude section 3 by saying that although for a very long time NPC topologies at 4 levels and beyond were considered to be unfeasible, because when applying conventional modulation strategies, this was leading to the collapse of some capacitor voltages, the introduction of virtual vector pulse width modulations and similar modulation strategies have enabled their use in any operating condition with any number of levels and for any type of conversion, whether it is DC to AC conversion, DC to AC conversion, or even AC to AC conversion, for example, by connecting back-to-back to DC to AC converters. So basically, they can be used in any application. Whether they are competitive or not is a different issue. In our research team, we believe they are competitive because on one hand, they have a potential for a high power density, since the legs are implemented only using semiconductor devices without any passive component. And on the other hand, we can adjust the voltage rating of the converter by using always the same switch and simply adjusting the number of levels, which allows us to take advantage of scale economies. Well, we will see if in the future this technology succeeds. It will eventually depend on the evolution, on the developments of this technology and the alternative technologies. So let's close here section 3 and let's move to section 4, where we will see some application examples. Okay, let's now quickly see a few application examples. We will first see how we can fit into a single FPGA the full control of a 4-level 3-phase inverter to drive a motor. Then we will see how we can configure an electrical vehicle traction inverter with lossless battery state of charge balancing. And finally, we will see how we can configure a photovoltaic system with an inverter that can control independently the voltage control of each solar array. Let's start with the motor drive. In this motor drive, a 4-level 3-phase motor drive, we will embed all the control into a single FPGA. The FPGA will include the modulation, the DC link voltage balancing control, the field-oriented control of the machine, and also the signal acquisition and the user interface. We will see the performance of this system through a video with an experimental demonstration. Let's start the video. First, we present the experimental setup. Here you can see the overall experimental setup. We'll get close. We have a look at the FPGA control board. This is the FPGA. You can see we have a keyboard and screen to introduce the parameters and watch their values. We also show the cameras that we use for the different images you will see. We watch the oscilloscope. This is the 3-phase 4-level converter, NPC. Here are some screens with the control of some of the equipment. This is, on the left, you see the machine that we use to generate the load torque, and on the right, you will see the machine that we control with the inverter. And this is the equipment we use to generate the full DC link voltage. In this first test, basically what we do is we calibrate the measurement of the rotor angle, and then we start the machine with a fixed speed. Here we are just simply calibrating, rotating a little bit the machine to calibrate the rotor position. And you can see that initially, when the inverter is off, the 3 DC link voltages are unbalanced. This is because the impedance across the 3 DC link voltages are different. We could fix this through a better design of inverter, but it is okay because as soon as we start the machine with a 300 RPM reference speed, you will see that the 3 DC link voltages get equalized. You see now they are all equal while the machine is rotating. When we stop the machine, they become unbalanced again. And it is okay. As soon as we start the machine, they get balanced again. Now we will set a reference speed of minus 500 RPM. So the machine will be rotating in the opposite direction. And then we will do some other tests where we will vary the load torque, and then we will produce a change in the rotation direction. First, we will change the load torque. We change it through this screen here. Now we are operating with no torque. We increase the torque a little bit. We will see that the phase currents increase in amplitude. We zoom in and we see that they are fairly sinusoidal. Now we will increase the torque a little bit more. Okay, now we come back to 0 torque, and now we will perform the change in rotation direction. We'll see that the image freezes to see whether they change the speed reversal, what happens during the speed reversal transient. Now the video is paused so that we can see the waveforms of the currents while changing the rotation direction. And we finally stop the machine. Okay, so we come back to the presentation. And now we will move to the second application, which is an electrical vehicle traction inverter using a multi-level NPC converter. Basically, here we configure our battery bank with a series connection of battery packs, and then we connect a multi-level NPC three-phase inverter to drive the electrical vehicle motor. And the nice thing of this configuration is that now we can control the power flow from each battery pack to the motor so that we can adjust the rate at which we discharge each battery pack. This way we will be able to achieve a lossless state of charge balancing control of the battery bank. To illustrate the advantage of this system, to explain it, we show here first what happens in a two-level inverter. A two-level inverter, what will happen is that the current flowing through the three battery packs will be always the same. This is okay if the three battery packs are the same and they have the same state of charge. But if one of them is different, it has a different nominal charge, or if the state of charge is different, this situation will lead us to a point where one of the battery packs will be fully discharged while the others still have energy, and we will not be able to take advantage of the full battery bank energy. With the proposed system configuration, the idea is that we will be able to produce different battery pack currents so that we can discharge each battery pack at the optimal rate. We will be able to produce these different battery currents because we are able to inject neutral point currents. So the neutral point currents, I2 and I3, will be defined so that we can balance the state of charge of the three battery packs. And we do this through two closed control loops, similarly to what we saw in section 3. Here in this experiment, we can see that we can control battery 2 current to be smaller than battery 1 and battery 3 in case we want to discharge this battery pack at a lower rate, and we see no distortion in the line-to-line voltages and phase currents due to these different current flowing through the three battery packs. Also, we see a simulation where we are simulating a full battery bank discharge process under an initial imbalance in the state of charge of the three battery packs. While two of the battery packs start with full charge, with a state of charge equal to 1, one of them, battery pack 2, starts with 80% of the charge. If we disable the control of the inverter, that is, if we operate the system like if we had a two-level converter, what happens is that battery pack 2 reaches a state of charge equal to 0, while battery packs 1 and 3 still have 20% of the charge. And at this point, we will have to stop to avoid damaging battery pack 2. But the problem is that then we don't take full advantage of all the energy in the battery bank. Instead, if we turn the control on of the system, what will happen is that the state of charge of all three battery packs will be equal at some point, and we will be able to discharge fully all battery packs so that we can extract the full battery charge the full energy of the battery bank. In this simulation, by enabling the control, we obtain 15% more energy. And the last example we will see is a photovoltaic system where we have a set of photovoltaic arrays connected in series, and we want to send the energy generated by these photovoltaic arrays to the grid. We do it by connecting a multi-level NPC inverter. This system will enable us to independently control the operating voltage of each photovoltaic array so that we can force them to operate at the maximum power point. Let's us explain the advantage of this system configuration by analyzing what happens in a two-level configuration. If we set the system to operate with a two-level inverter, what will happen is that the current flowing through the 3-volt photovoltaic arrays will have to be the same. Whenever we have full irradiance in all photovoltaic arrays, this is not a problem because the current that is flowing through all of them is the same, and we will generate the maximum power that these photovoltaic arrays can generate, no problem with that. But as soon as one of the photovoltaic arrays, for example, is under shade, since the current that is able to flow through this photovoltaic array will be limited, this will also limit the current flowing through the other photovoltaic arrays, even though they receive high irradiance. So overall, we will be losing quite a lot of power compared to what we could generate if we were operating these photovoltaic arrays independently. One solution to improve things here is to add bypass diodes through the photovoltaic arrays so that whenever a stronger current is generated by some of the photovoltaic arrays with higher irradiance, this current can flow through the bypass diode and still then produce the high power generated by these highly irradiated photovoltaic arrays. But even in this situation, we will be losing the power that the shaded photovoltaic array could generate because all the current is flowing through the bypass diode. And if we have more than one photovoltaic array in shade, we will be losing more and more power. So in the proposed configuration, we will not face these problems because we can adjust the current flowing through each photovoltaic array so that they are different. If all photovoltaic arrays get the same high irradiance, no problem, we will make them all operate with the same current. But if one of them is in shade, we will be able to inject neutral point current so that this photovoltaic array operates with low current while the others operate with high currents. And still we will be able then to generate the maximum power possible. To operate the system, we need to first set up 3 control loops. One of them is regulating the total voltage of the photovoltaic arrays. And the output of this control loop will be the command of the power being delivered from the photovoltaic array to the grid. And the other 2 control loops will control the voltage imbalance at DC link points 2 and 3. All these 3 commands, in fact, are defined based on the commands of the 3-watt photovoltaic array voltages. And then through MPPT algorithms, we could find out the combination of these values that produces the maximum power. Here we show the results we obtained in a facility we have in our building, where we had 3 photovoltaic arrays connected in series, 2 of them receiving high irradiance and the other one with a little bit of shade. We tested the system with the control off, which aims to reproduce a two-level inverter without bypass diodes, and also with the control on. And we saw that by enabling the control, we were generating 30% more power. Well, and with this, we finish with the application examples. I want to thank you very much for your attention. Please contact us if you have any comment or question, and stay safe and see you soon. Bye now.